LTE Advanced Part 1. Here we will first start off with ICIC and FFR. ICIC stands for Intercell Interference Coordination and FFR stands for Fractional Frequency Reuse. ICIC alleviates data rate degradation at cell edges due to intercell interference by FFR. Now that's a long sentence, may be difficult to understand. So let's make it a little bit easier using an illustration. You can look right here where when you go to the cell edge is where the performance is the weakest. In the middle of your cell, which looks like honeycomb structures right there, the middle of the cell is where they have the green colored region. And as you can see here in these figures, the green region, the green level is lower than the blue, red, or orange levels, meaning that it's using a lower power. It's using a lower power near the center of each cell because that's close to the base station where the reception is good. The signal to noise ratio is good. So therefore, you can get away with a high quality data service using very weak powers. And that's why the green levels are all low. But when you want to support high quality data communication at the cell edges, you see that the power level of the blue, the red, and the orange are higher than the green levels. So they're using stronger power at the cell edge. And once again, mobile communication is so difficult at the cell edge. So that is why when I do research with my engineers in my laboratory, handover, which is one of the most difficult performance measures to conduct, to provide high quality services, that's what we focus on a lot. Because if you can provide high quality services during handover, you can provide it anytime, anywhere. Because those are the weak points, the bottlenecks, the Achilles heels. Let's look into this part where follow this arrow. That arrow leads to a point where three cells are meeting at a corner. If you look at the end of the arrow, you can see an orange region, a blue region, and a red region there. That means that they're using different frequencies. This is where FFR kicks in. FFR, fractional frequency reuse, separates the frequency bands and allocates the band efficiently to prevent signal interference from adjacent E-node Bs. Looking at the position where, at the edge of a corner, you see a blue, orange, and red region nearby each other. You look at this figure right here, you can see that the blue region, the red region, and the orange region have stronger power, but they are at different frequency bands. Look at where they are located on their individual frequency axes, which is the horizontal axis. They're located in different positions, meaning that you're using strong signals because the blue, red, and orange are all stronger than the green level. But in addition, they are located at different frequencies, so they do not interfere with each other. That is what we mean by FFR. And putting this together is intercell interference coordination. DSA, Dynamic Subcarrier Assignment. This is an improved resource allocation scheme upon static allocation that dynamically allocates subcarriers considering channel state conditions. So you're going to look at what's going on, where are the locations that some channels are weak and cannot receive, where are the null points in the spectrum, and you take advantage of that to support other users in those areas, such that the interfering level with that device, since it's in a null anyway, and it can't listen to anything, you can go ahead and focus your signal on that area for another user and get a large gain out of your communication link. For example, look at this. Here, user 1 is in the blue line, and user 1 has a spectrum null over there. User 2 is in the red dotted line. The red dotted line has a spectrum null right over here. So what we're going to do is this. Since we know the spectrum and where the nulls are for user 1 and user 2, what I'm going to do is this. I'm going to allocate user 1 to focus its communication where its neighboring device user 2 has a null, spectral null. That way, even though a strong signal is sent to user 1, user 2, it's in a null anyway. It cannot receive anything. That's where the spectrum is weak. So it cannot read the signal, so it will automatically not see the signal of the other user. It will not show up as a strong interference. Taking advantage of this is what we're doing in DSA. Once again, you can do this because LTE Advanced technology is adaptable in the way that it can allocate the frequency bands to certain locations. That's why it can achieve such high data rates. Due to frequency selective fading, subcarriers have different effects on users, which you see different null points in the spectrum for different users. Thus, DSA can improve the user quality of service in various ways by tracking the overall spectrum null points per user and then using the adaptive control assignment mechanism that is assigned within DSA technology. Pretty cool, isn't it? COM, Coordinated Multipoint Technology. This improves the coverage of high data rate, cell edge throughput, which is where we have our weak point, and system throughput. You may see multipoint with a hyphen or without a hyphen, and you will see both in various documents. So consider them the same when you see comp. It is like this, where you have multiple cells supporting a base station together. You have multipoint means multiple base stations are pointing at the same device, coordinating, that's where the word coordinated comes in a way such that multiple eNodeBs communicate with a UE at the same time to increase throughput by reducing intercell interference. There are a couple of ways to do this. Coordinated scheduling is one, CS. Coordinated beamforming, CB, is another way. Joint transmission is another way, JT. And dynamic point selection, DPS. These are the four major ways to do it. Let's look at one by one. Coordinated scheduling, CS, is like this, where it allocates different subcarriers to UEs at the cell edge. Once again, at the cell edge. This is where we have to enhance our performance to avoid intercell interference. You can see right here, for that device that is at the cell edge, we are using different frequencies. Frequency 1 and frequency 2 are both used to support that device in the middle. What this means is that that device that is at the cell edge in the range of handover is in need to receive both signals in order to get comp support. This may require that device to have multiple modems, such that one modem can be set to frequency 1, the other modem on it can be set to frequency 2. And these both modems must be able to be turned on and processed at the same time to take advantage of comp technology in LTE 4G. Then we have CB, Coordinated Beamforming. Once again, we are using multiple antennas, array of antennas. And when you have multiple antennas, you can do beamforming. You can make it a directional signal, where instead of omnidirectional spreading of the signal, you can use multiple antennas to focus it into a beam, a wireless radio frequency beam. And that is what we mean by beamforming, but it's coordinated to serve a purpose, like this, where you allocate different beam patterns to UEs at the cell edge to avoid interference and also improve the reception performance. Where you see right here, there is a nulling effect for the beam pattern 1 and beam pattern 2. You're supporting different devices at the cell edge based upon different beam patterns. This is what we use in coordinated beamforming. Very effective and possible because we have multiple antennas, an array of antennas that we are capable of steering, beamforming. Then there's joint transmission, where from this base station and the other base station, they are coordinating their signals together such that the UE, the user equipment device, your smartphone, for example, is receiving both and supporting communication at high data rates. This improves the reception performance by having the UE receive data concurrently from multiple E node Bs. Then there is dynamic point selection. This selects the transmission point with better channel quality to improve the reception performance. Here we will say transmission point or TX point. You will see either TP or TX point based on different documents that you may see. Basically, they're talking about the transmission point. And this is used very frequently in DPS technology for comp in LTE 4G. Let's compare them a little bit side by side since there's 4 of them, and here we go. There's CS, CB, JT, and DPS. Resource-wise, it's frequency for CS, frequency and spatial diversity for CB, the same for JT, where DPS will use spatial, time, and frequency all coordinated together. The number of TPs. In CS, CB, it is all single, but for JT and DPS, it's multiple TPs are used. Decreases interference. In CS and CB, this is where the interference decrease effects are obtained, but for JT and DPS, not that much. On the other hand, reception performance-wise, CS is a little bit lower compared to CB, JT, and DPS technologies. These are the references that I used, and I recommend them to you. Thank you.